Today, we're going to talk about some 3D printing and how we would use it for Pearadox. And so this is a very brief overview. You're not going to necessarily be an expert by any means after this presentation, but hopefully it introduces you to things and makes it seem much more approachable so that you can go off and learn some additional things that you need or ask questions when you get to a point where you want to do some 3D printing of a part. So I think one of the important things is knowing about our objectives. So I want to make sure you know when it makes sense to 3D print things, what 3D printers we have and which one you should use for various things, and some general terminology and how to start. So I think the first question is understanding why would we 3D print anything? We've got a CNC router, we've got a mill, we've got a lathe. What's the purpose of 3D printing in our situation? So it's relatively cheap. It can allow for rapid changes in prototyping, and it can be manufactured when we're away from the shop. So what I mean by that is lots of students have a 3D printer at home, or we can start a print and then leave and then come back the next day and now it's done. Most of the time we're away for at least 8 hours, usually plenty more than 8 hours as well. So 3D printers can finish a job during that time. And also, you just don't need the strength associated with metal or polycarbonate parts. And even with a 3D printer, you can do polycarbonate or what's called a carbon fiber infused like nylon that's really strong still. So you can still have really strong 3D printed parts. I say it's relatively cheap just because sometimes, obviously, if you're doing big prints, those can be expensive as well. But compared to most of our, when you look at all of the resources involved of time and the physical components and using one of the things that we only have like one of, like the mill or router or whatever, it's pretty cheap. So I think there's some really interesting use cases for 3D printing. One of the really cool ones that we can pull on of a specific FRC team is 125 in 2017 did a 1/3 scale of their fuel hopper to really optimize how fast that works. So I'm going to pull up their album that they made here. So the game piece in 2017 was these fuel. It was, I think, a 5-inch ball, wiffle ball. And they found one that was nearly a 3-to-1 scale. So it was 3 times smaller than this guy. And it meant that they could 3D print really small things, figure out a bunch of geometries to make their hopper work the way that they wanted it to, and then go off and build a real one and feel pretty confident with it. I'm sure any of our veterans can tell you, even when we try to do a quick and dirty prototype with, say, plywood and 2x4s or polycarbonate, it can be really rough. It can end up taking a long time. And then all the kind of like things that we do to hack it together make it not work as real or well as a real one. So being able to 3D print something can be really useful. So they've got some cool examples here. If you want to go and look at this, they were basically looking at how I think a die hopper or die rotor, I forget exactly what it's called, works in a like paintball gun to be able to sort all that stuff out and shoot out the paintballs as quick as possible. And so they tried to take that concept for fuel. And so their first thing was just printing on their printer, a small thing. And their intent was to actually rotate, I think, the outside hopper of it as well. You can see they've got basically a hook on the inside. This guy here has got a hook that goes around the edge. And when the two are moving in opposite directions of one another, it forces it up the center and through the top. And so you can kind of see in here, this was their first test with it just to make sure that the concept was sound. It was grabbing the balls the way that they liked it. And so, and pushing it towards the center. So they were happy with that. As you can see, the final intention, the intention of the final version was to have the hook and cage counter rotating. And so then they did a full feed prototype here. And so you can see, again, I think it was maybe hand powered where they were turning it and just seeing that when they had all these balls in here that it would push it up out the center and be able to get them all. And then they realized like, okay, well, we need to do, make it a little bit more good. And so they added a little bearing in here to help because they were getting stuck in here and you can only do so much with the printing geometry. So already this was helping to pay off. They identified a potential stick point, and I'm sure in their real design they had something to help prevent it from sticking in here. They kept on going. You can see they kept building different designs and checking it. They were pretty happy with it. This was a self-powered prototype, so they moved it by hand. And they were pretty, again, just moving forward and seeing that it was collecting the balls and pushing it out the center. It wasn't jamming up, anything like that. They eventually tried to power one with a bag motor. I forget exactly, but I think it said that they had trouble getting to actually be powered and work the way they wanted it to. So then they started moving on to the full scale. This was their first full scale version powered up and running. So all those 14 prototypes that they did at 1/3 scale paid off to be able to make this work much quicker. You can see that obviously they have like a wire going around there. So it's still pretty early in the prototyping process. They had to address some other things. And then the rest of these images kind of help explain a little bit more about how their die hopper worked. Really cool outside of the scope of what we're talking about here. But we'll go ahead and watch some of the GIFs of what they, yeah. So hopefully y'all can see this, but that's just insanely fast. As far as they are aware, and as far as I'm aware, they had the fastest ball throughput of any team in 2017. They could clear their hopper very quickly. And then this one should, I think, also show, you'll see in the bottom left-hand corner there, just a crazy throughput. I actually would have been concerned that the throughput was so high that their shooter reel wouldn't be able to keep up and they wouldn't have a consistent shot, but they definitely made it work. All right, so that's an example of using 3D printing at prototyping scale. Also, you can design and manufacture parts that would be either very hard or very expensive to do with normal subtractive methods. This is not a very functional picture for anything that we would do, but it helps show it. You could make this sculpture in the middle much easier with a 3D printer than you could if you were trying to do it on a mill or lathe or CNC router or anything like that. Hopefully that's kind of obvious from even the looks of things here. And of course, it's also useful for keeping things lightweight. Some extra background, I'm not going to go through all of these, but hopefully if you find this interesting, you'll go and look at some of these links. As a reminder, I always put this in the meeting recaps, so you can go off and find this later. But Markforged has several blog posts about designing for 3D printing. You talk about unit tests and tolerances, which we'll talk a little bit about. Some part warping, which we'll talk a little bit about, embedded nuts, which I probably should talk about more than I do. Heat set inserts are really great and important. And then you can do some really cool things like casting custom wheels in 3D printing, embedding components in 3D printed. That's I think something worthwhile doing. We did that this past year with embedding some bearings in our pulley. And then threading joints and some other things here. There's also some interesting stuff about nozzle diameter effects. So this is a video that if you want to learn a little bit about the difference between using nozzles with different diameters, if you're not super familiar with printing already, and it compares doing the same print at and the time that it would take with various nozzles, or what the quality and detail is, and all that other kind of stuff. So that can be interesting if you're kind of new to 3D printing. So I'm going to try to quickly recap the 3 printers that we currently have and some of the filaments that we commonly use. So one of the printers that we have is a Monoprice Mini Delta. It is the cheapest of all of our 3D printers. It's also probably the lowest quality one that we have, unsurprisingly. You're probably not going to get the same kind of tolerance holding with the Mini Delta as compared to the Prusa or Markforged. But it is great for printing just small things like spacers or pulleys or things like that. We have printed PETG with it, which is a filament that I'll talk about later. But PLA is the filament that works best with it. One of the really nice things about the Monoprice Mini Delta is that there's 2 different documents that are just full jam-packed with information about the Mini Delta. So you can become a real pro on it and know how to just do everything you can to increase the quality of the print. So there's one that's the Mini Delta 101. And so it goes through a couple of the things of like how to tune the belts to make sure that one of the interesting things here is that because it's got just these 3 points. All 3 of them have to work together to move in just one direction. And so you need to make sure that the belts have equal tension. And so the way that the community has discovered to make sure that the tension is equal in all 3 belts is to tune them like they're guitar strings, basically. And several other things to help make sure you get a good first layer and things like that. So the 101 document is really great. There's also this calibration roadmap that suggests different upgrades to do, some frequently asked questions and troubleshooting tips. So if something's not working with a Monoprice Mini Delta, we've got these 2 documents full of information to help us. If we need to use a bed adhesion, I would recommend that we use this guy here. It's called it's a nanopolymer adhesive. Basically, you squirt just a little bit on it, and then you take the brush and smear it. And what this does is it helps make sure that the filament, when you're printing it, gets stuck to the bed so that it doesn't lift off or anything like that. And so it's not always needed, but it's something to keep in mind if we are having any kind of issues with it. The Prusa is the other, I don't know, more simple 3D printer that we have. And so this is, it's more expensive. To give you guys a comparison, the Mini Delta was on the order of like $100, and the Prusa is more on the order of $1,000. So obviously the Prusa, you should hope that you get better quality all around, or better ease of use. It is, I think, very easy to use. The software that you use with it is very straightforward to use, I think. And it works very well. Typically, you can kind of set it and forget it, and you don't have to pay too much attention to it other than some common maintenance that you should do between prints. It also prints PLA, PETG. We don't do anything with ABS, but it can do ABS. If we put the appropriate nozzle in it, we could do a filament called Nylon X, which is a very strong filament on par with our other strongest printer that I'll talk about in a second. You can get pretty good quality prints. The bed is much larger than the Monoprice. I didn't put up the comparison, but it's relatively easy to set up and use. Again, you would use the nanopolymer adhesive, and there's some good information with regular maintenance. I thought I made this a link, but I didn't. But this kind of talks about the things that you would typically do. One of the things that is important to do with this is when you're done with the print, this is actually a magnetic bed here. So you would take the bed off, and then you'd kind of flex it a little bit to pop the part off. Or if you need to, use one of our scrapers to gently scrape it off. And then you can wipe it down and put the magnetic bed back on here. It's really important that you never do a print without the magnetic sheet on here. There's 2 different kinds, and one's better for PI or PETG, one's better for PLA, but we can talk about that some other time. And then our last 3D printer that we have is the Markforged. It's the most expensive. Just to add a cost value on this, this is more on the order of like $4,500. So each printer, as we've gone through here, has gotten more expensive, but also you can expect better quality with it as well. So with Markforged, we print something called Onyx, and I'm realizing I probably should have switched my slide order around and have the filaments before the printers, but hopefully this is okay. So Onyx is our strongest filament. I'll talk about that in a couple of slides here. Before you do anything with the Markforged, you should always have a mentor kind of review your setup, especially if you're new to it. Once you get to a certain point, I'm sure we can let people start the print without having to worry about it too much, but it's easy to end up wasting filament, and it's just very expensive, and it would be good to do a review. So before doing a print or before the build season, we should do a check to make sure that the bed is level, that we do an under extrusion check. And during the season, even, we should do a couple of bed levels every now and then, make sure that all of it's level. And after every print, this bed is also removable. You can remove it, wipe it down with just some water and a paper towel. And what you do with this is you use this Elmer's glue stick, which is purple, this disappearing glue, and you just put a little bit, you smear it across where it is that the print is going to happen. And we'll talk about bed adhesion and why you do that in a bit later. Any questions so far? I like the idea of a checklist for the setup, and I've thought about different things to do for that. Maybe that's something that needs to go in the It Needs Doing channel. So good suggestion there. So to talk about the actual filaments, some of the common ones that are more cheaply available and likely to have at various homes amongst your peers here is either PLA or PLA plus. It's very common. It's very cheap. You can get PLA rolls as cheap as like $15. You can also, spend a little bit more, like $20, $25. It's generally good for us to stick with the same brand because each PLA or PLA plus the optimal settings for printing can change a little bit. Even changing colors because the color pigment or whatever it is can make it where it prints a little bit better, a couple degrees warmer or colder than other colors. So I can't remember exactly, but I think, for instance, like black and white are the two extremes. Maybe I forget, whatever one is with no color added, basically, like it prints, I think, at a slightly lower temperature, or maybe it's a slightly higher temperature, a little bit better. But anyway, so printing a solid 1-inch cube only costs about 52 cents. So again, that's relatively cheap. It prints really easy, especially the PLA, but even the PLA Plus is pretty easy. And then there's PETG, which is about the same price as PLA. It's stronger than the PLA, but it has a higher melting point, and so it can be a little bit trickier to print sometimes. The Prusa does it just fine. The Monoprice not as good. And so we can do plenty of PLA and PETG all day without much problem. And it's just a matter of how you print it and to get the optimal strength. We don't really do anything with ABS, so I'm actually going to skip over that for now. I copied these slides from something else. All filaments are very susceptible to being ruined by moisture. So if we are not actively printing or we're not going to be printing for a few days, they should be put in a dry bag. If we're just going to leave overnight and come back the next day and do some printing, or maybe in the day or two, that would be fine. But if they're left out for a long time without being in a dry bag, that filament basically absorbs water and then it just won't print well anymore. So either the prints will fail, you can get some problems with your setup, or it'll just be extremely brittle and you won't really have any good strength. You can recover most filaments in basically by putting it in an oven. You can either put it directly in a real oven, or you can, I've got a dehydrator that you can put it in and run it for several hours. But just generally speaking, if you're smart and put things in dry bags when you're not using it, then you're pretty good there. And a dry bag is just basically a giant, gallon size type Ziploc bag. Most of the time, a gallon size bag isn't big enough for the rolls of filament. And then you can put little desiccant bags in there to help absorb any moisture. But those also have a shelf life. Once they've absorbed a certain amount of moisture, those bags won't work anymore either. So hopefully that makes sense. Definitely, if I'm saying anything that doesn't, please let me know in the chat. And then Onyx is what we use for the Markforged. So just as a comparison, these rolls are about $20 for a whole roll, a whole 1 kilogram roll. This is more like $200 per roll. And so a solid 1-inch cube, if you were to print a solid 1-inch cube, it'd end up costing $4. So you can see obviously that that's part of the reason that we would want to be smarter with our filament and how we do anything with that. It's definitely the strongest between PLA, PETG, or PLA Plus. It's a lot stronger. If you've got the Markforged set up right, you won't really even see any like layer lines. The way it fuses together, it can come out with some very good looking parts. It contains carbon fiber, which is a big reason why it gets its strength. But it is extremely susceptible to moisture. So whereas our Prusa and Monoprice Mini Delta, you have the PLA roll or PETG roll just out and exposed to the air. And it's just like if you're not doing anything with for a while, you want to put it in a dry bag. This actually stays in a box the entire time and has a special port where the filament comes out and it stays in a tube. And it's pretty much only the filament that's exposed to the print head area and some of the other parts there that are exposed to open air. So it's very important that this stays in a dry bag. If you ever need to open up the dry box, you don't want to have it open for more than a few minutes. If you open up a new bag of Onyx, you want to get it in the dry box in like 10 to 15 minutes tops. So it's not something you like open up a bunch of them and stack them and leave them there, or it's not something you like open it up and then go get distracted. And then the Thrifty Bot's putting out a couple of cool videos about Markforged stuff. So good filament will snap easily. So if you want to see, my college friend Ryan here has a video here. So he's showing that he had some old filament that had absorbed moisture. And so you can see what he was bending it here. I think this is the older one, so it's not really snapping right away. It's just kind of bending. Maybe it snaps a little bit at the end, but then he's got his new filament here. And so you can see that as he bends it, it snaps very quickly. So this is good filament, the kind that snaps right away. So you can see how much of a difference getting that moisture in can have. Lastly, there's Nylon X, which is very similar to Onyx. It is cheaper than Onyx, but more expensive than PLA PETG. So for instance, a solid 1-inch cube would cost $2.25. It does require a hardened nozzle in the Prusa due to the higher temps. So you can get either ruby tipped nozzle or something called Nozzle X, or there's probably various things out on the market that you can get. It's also very extremely important to keep it dry, much like Onyx. So we haven't done anything with Nylon X for a while. If we ever get enough money that I decide to buy a second Prusa or anything like that, I might set up one Prusa specifically to use Nylon X if we wanted to. That would be probably my next goal with 3D printers. All right, so the filament guide, there's a YouTube video you can watch here that goes over a bunch of stuff. I'm spending a lot of time on this. I apologize to everybody. I'll try to kind of speed it up and get to some of the exciting stuff. So the Slicer program is the software that you use to import a STL. And an STL is kind of like a step file. It's just your file of your 3D part that you've designed in Onshape or something like that, or you downloaded from Thingiverse that you want to print. So you import the STL into your Slicer, and then the Slicer actually turns this into a bunch of layers and saves off information for the 3D printer to go print. So we'll do an example of that in a little bit. And it creates something called G-code. So G-code is used for the CNC router. It's used for the 3D printer. G-code's kind of a common thing to tell a machine how to move, like XY locations or different commands. So we actually unfortunately use 3 different slicers for our 3 different printers. So we typically use Prusa slicer for the Prusa and Kira for the Monoprice Mini Delta. You could probably use either one for, you could probably use one slicer for both of them. I just haven't had as much luck with mixing them. And then we have to use Eiger for the Markforged, and I can go over that sometime if desired. Infill is hopefully pretty self-explanatory. It just tells you how many or how much material you're putting between things. So the more infill, generally, the stronger the part. There does kind of reach a point of diminishing returns where you're just kind of wasting filament. But hopefully this makes sense. You can do lots of different patterns. This one for here would just be, I guess, a rectangular one or a square one or whatever. But you can also do honeycombs. You can do a gyroscope or I don't know, some kind of like wavy thing. You can do triangles, whatever. Perimeters or walls are these green lines on the outside here. And so the more walls or perimeters that you have, generally the stronger the part can be as well. So you can do a low infill and add some additional walls to get extra strength. And so if you're finding that, you know, you've got a big part and you don't need a lot of infill, but maybe you just want to increase your perimeter walls a bit to help give it some strength. And walls can be very useful when you're trying to put in like a bolt or something like that. So say that you had a hole here and you just had one perimeter or one wall or whatever, then it's just going to be one circle here versus if you've got 4, you'd have, you know, a circle and growing circles outside of it. So when you put this threaded insert or a heat set insert into it, it would have more material to grab. So having the right number of walls is important. Supports are pretty self-explanatory. If you have something that's coming out at a sharp angle, if you just tried to 3D print it, it's like printing it out in air. So obviously it's going to droop and kind of sag and not go anywhere. So you can print out these supports so that it basically has something to land on, and then you can break these supports off afterwards. PLA supports break off very easy. PETG is a little bit tougher, and Onyx, of course, is also tough as well. And so generally you want to design to avoid supports or put things on the plate and slice it in a way that you don't need supports, but that's not always avoidable. Rafts and brims or skirts are also different things that you can do to help out with things. So if your bed's not being perfectly level, and you can kind of cheat a little bit by using a raft or to help raise it up, and then the bottom of your part will be on the raft rather than on the print bed. The brim is useful if you have kind of like a tall, skinny part. You can add brim layers around it so it's got more stuff kind of making it stick to the plate. And then the skirt, I'll be honest, I don't really understand why the skirt's there first. It helps, I guess, by priming the nozzle, so you can add some material down and make sure you're getting part material extruded. But I don't think it's useful other than having like 1 or 2 layers of skirt, or really just 1 layer of skirt. Layer height, we don't usually need to mess with this very much. We've got profiles that we can set. It basically just says how much detail you can get out of it. So the smaller the layer height, the more detail you get. So you can see this is a very small layer height, but it takes a lot longer to print, versus you do a bigger layer height and then you can very clearly see where the layers are. Bed adhesion is very important. The first layer is pretty much the most important layer of your 3D printing. If it starts to lift up, that can be for a lot of different reasons. Maybe you didn't use either the Elmer's glue or the nanopolymer. You can also use like hairspray or blue painter's tape, but we usually use the glue or the polymer. If it's coming off, it could also be because the bed isn't level or it's not clean. It could be that the AC is blowing across it, so one side's cooling much faster than the other, and as that cools, the part shrinks or whatever, things like that. You can use the brim, like I said, to help with warping if that's an issue, or you can use a raft if it's an issue. But really, you should try to identify the root cause, and the brim and the raft are kind of a cheat to get around it. Print speed, you don't need to worry about too much. We'll skip over that for now. The nozzle is also, we don't need to typically change very often, so you can look at that later. Heat set inserts, this is a great video that kind of explains how you might use them. So basically, if you have a printed part and you want to be able to bolt things into it, it's really great to use a heat set insert. This video in here somewhere, I think, oh, maybe it's not here. Basically, you take a soldering iron and you heat up this, here we go, you can kind of see here. So you've got your 3D printed part, and then you heat up your soldering iron and you push the insert, this threaded insert, into the 3D printed part. This plastic melts around it, and then it can hold it, and you can bolt things into it and get pretty good hold force to it. So I'm finally into some things for designing for 3D printing. Let me see, I've only got 5 slides left, so I think we can still finish close to on time. So the print orientation is something that's very important, and I'm going to kind of I've got some additional slides after this that talks about it. But when you're designing for 3D printing, you want to think about what your print orientation will be. You want to minimize the number of supports that you need to use via design decisions. So you want inclines that are like 40 degrees or less from vertical. You can have them, like it's not bad to have them, but if you can avoid it, it's definitely preferred. Sometimes you'll need to split up the part into multiple parts, either because the bed's not big enough, or maybe you just want to be able to have multiple prints going at once, or you think one part's more likely to break. Well, I don't know, there can be lots of reasons for splitting it up into multiple parts. And then another really important thing to keep in mind is that 3D printing tolerances are going to be a little bit different. So plastic expands as it cools, so that impacts it. The nozzle and stepper motors can only produce so much detail. And so it's kind of a common problem that if you put a hole in something, it either is too big or too small. So if you're trying to 3D print something and have a bearing put into it, typically what we would do is, you want a 1.125 inch bearing hole. But if you print that, you'll find that it'll end up being too small. And if you try to press it in, the bearing won't work very well, or you'll print it and the bearing will slip right into it, but it'll also fall right out because it's not going to be a good press fit. And so there, when you're designing, you need to keep kind of things in mind as to how you can manage that. So I've got a couple of slides that I'll talk about ways that you can deal with some of those 3D printing tolerances. It's also can be useful to have rounded corners versus sharp corners. When you've got a sharp corner, your mechanical engineers on the team, which I think is like Kara, can tell you about how thermal expansion can be really harsh at sharp corners. And so that can cause warping and make some problems there. It's not typically too bad of an issue, but it is something you can keep in mind. You can kind of see here, because this is at less than a 45-degree angle, it doesn't need any supports when you print it. And so it can print up here and it comes out just fine. It looks pretty good. There's the H here, which this has something called bridging. Bridging is totally okay. You can bridge things as long as it's not too long of a part. Basically, you print it along here and then you come across far enough and then it catches over here. And so you'll get some droop or some sag in here, but maybe it's some, for what we do in FRC, it's typically okay to have some of that droop in there. It's just a matter of managing how big of a part that you've got here, or how big of a bridge you've got. And then afterwards, we would just want to go clean that up and remove any stray strands. The issue would be is if during this bridge, you've got a hole in the middle, it does a circle in the middle first and it's not printing it on anything. So I'll talk about that in a minute. And then the T here, it's not bridging, it just prints out and it doesn't have any support on the end over here. So you can see this gets really ugly. Again, for what we're doing, maybe it's okay. And we just got to clean that up afterwards, but you can see you're not going to get a 90-degree here. You're going to get a little bit of a slope. So it'd be better if you just kind of designed it such that as you're printing and you're coming out, you just bring that slope in so that like it doesn't print so ugly. You can end up with a failed print because it can't do anything there. They're probably a little bit lucky that this worked out okay. All right, so print orientation. So I want to do some live examples here in Prusa Slicer, but I've got a couple of things here to talk about. So this, for instance, is the prototype stuff that Spectrum did. So you can see that on the left here with the check mark, they suggest that you print it with a C in this orientation versus the C in this orientation. So if you do it like this, the layer adhesion, or between the layer adhesion is the weakest part of the print. So if you can imagine, you've got all these layers and it's all going parallel here. And if you get any force that's trying to bend that C, either close it or expand it out, you're putting a lot of stress on the adhesion between the layers and then it'll break. Versus this one, the layer adhesion is along the whole path here. And so if you were trying to bend this clamp, either bend it closed or open it up, it's got the whole one long continuous strand coming along. And so it'll be a lot stronger. Instead, the layer adhesion, it would be like if you were trying to take the short width and pull it apart that way. I don't know if that makes sense from my explanation. Definitely feel free, if it doesn't, to drop something in the chat, but we'll talk about some more in the live example that I do in a little bit. I've also got some examples here. So this one seems kind of silly, but hopefully it'll make sense. So this is a case for a SRX magnetic encoder. And so this would be an Eiger on the Markforged, was where I was printing it. And the first time I printed it, I actually printed it so that this side here was at the bottom, because you could do just shorter support here. And then on the other side, you've got a lot of things that come up and it's not a big deal. And so I did that because I wanted to minimize how much support material was used. However, I printed it and I realized that, like, man, the magnetic encoder goes in here and it's really hard to remove that support, versus this is the outside of it and I don't care if it's ugly or not. So instead, when we would print this part, we'd actually print it in this orientation, which increases the amount of supports, but helps keep this area clean where the encoder would actually have to sit. Similar situation here, the encoder sits inside here. And so you've got this bridge here, but we could try printing it and just see how the bridge turns out. Or if we needed to, we could add supports and then just rip this support off. I'll do the Prusa slicer example at the end of this. I feel like I skipped a slide here. Oh, okay. So you can also set up your parts to split up in multiple parts. So I've got 319's 2020 turret up somewhere here. Here we go. Oh, of course, it wants me to refresh it. All right, so their turret here was just one really big part. So you can see it's meant for a belt to go around, but they don't have a 3D printer that would be able to print that big of a part. And so you can see that what they did is they basically derived their turret part here. So they pulled in their part, and then they did a sketch. And it's a little bit tough to tell. It's sketch 2 here. This orange line that is a little bit hard to see. They did a sketch there, and then they were able to separate out their parts with the rest of their stuff. And I don't know what, there we go. So you can see now with that sketch to separate those two parts, now they've got 4 distinct parts. So they've got turret pulley, right, left, front, and back. And so they could print out 4 individual parts, and then they would stick a bolt together to hold it together and clamp them. The other nice thing about it is that if they broke a turret, they wouldn't have to reprint a whole thing. If for some reason, like just one of these sides broke, they could have those spares on hand and not have to replace the whole thing necessarily. So that's an example of splitting it into multiple parts. You can see that Onshape has some tools readily available or that you can use to do that. So they've got a blog post about that I think I meant to link in here, but I didn't. But hopefully that kind of makes sense. You can see this was one big part. Their printer could only do something that was 5 inches wide. And so they that added in a sketch here, and then they transformed and moved this and brought it out to a second part. So this is another example of the print orientation. So this is one of those things that it may feel a little counterintuitive if the print orientation thing makes sense. So these layers are all going across left to right here. And if you were to try to take that roller, and if the layer adhesion isn't really good, you could have it between your hands and kind of snap it like you would a pencil. However, because of where it is that it's going to be, and it's relatively short, and it's got a pin going through the center of it, it's not really going to take forces like that would cause a roller to break at the layer adhesion. So if you look at the Chief Delphi discussion from 125, where they shared their model for 3D printing these mini mecanum wheels, they discussed that they actually printed it straight up and down because they don't need any support for it. They get better dimensional control over the profile of the roller. So if you imagine that this was on the side, now you're getting a bunch of layers as opposed to like a circle. So you get a nice smooth roller here, which gives it a little bit, makes it a little bit more slick. Kind of like I said here, or this was just me adding this bullet point, you're unlikely to really experience forces that would pull the layers apart. So it's important to kind of balance all the different things, even though from a print orientation, the forces that it would see, it would be stronger if it's on its side. You don't really need to worry about that in this case. So for all the other reasons, it's better to print it upright. So there's a lot of more advanced things that you can kind of keep in mind. So I've got an example here. If you wanted something to be a 1/10 inch thick spacer, which would be 2.54 millimeters, and your layer height is 0.4 millimeters thick, then the real part would end up being 2.4 millimeters or 2.8 millimeters instead. That's a little bit of a lie because the first layer is a little bit different. But it's something to keep in mind that if you really need something to be dimensional or like have tight dimensional tolerance in something, you want to design it with those types of things in mind of what is your layer height, how many walls and perimeters you have, things like that. And keep in mind if your first layer height is going to be different. So I've got something I can share some other meeting if people are interested with an idea that somebody on 1885 is doing to try to do that with variables and Onshape, which I think is a neat idea. Some other things. So this is where we could really get into some more things. And so if you'll want, I can kind of pick up from here next week. But there's a lot of things that you can do with 3D printing. So we could basically end up watching all these videos, or I can just share it in meeting recaps. But you can do these sacrificial bridges. And so if you can imagine when they did this design, this would normally be a hole through here, through the middle of this bridge. And so that was, I was talking about, if you tried to print, it would do a round circle right in the middle here on nothing. And so if instead you make a thickness, that's the thickness of one of your layers, you do a bridge and the bridge comes out fine, maybe a little bit of droop, and then you build up your circle on top of that. And then all you need to do is like clean this one hole up with a drill, and it's only one layer thick. So you can, you know, get a drill bit in there pretty easily, or however else it is that you may want to do that. So you can do a sacrificial bridge like that. You can also do sacrificial bridges in other ways. Of course, this is, I've got an ad here. Let's see if they've got, I think this just keeps talking about the sacrificial bridge. So you can see in this type of part, maybe they want the hole to go all the way through. And so they've just got something that's got some thickness here to be able to get a whole bridge across and be able to print up. There's some alternatives to sacrificial bridges. And so this is a really neat video about what he did for that. If it will let me play it. And it's again, basically just being smart with your design to be able to kind of mess with the slicer settings and all of that. So these are all neat things to go off and learn about for more advanced designs. Something that I've only recently been exposed to is the idea of doing these crushed ribs. I've seen this used at NASA for plenty of mechanical things, but basically what you end up doing is, if you could look at this part very closely, you'll see that it's printed kind of at a slight angle, and then there's these round bumps here. And so the intent is that that gives you your interference, and these could kind of crush, and so that you could maybe get a bearing in and it would actually be a press fit, or more of a press fit or whatever. And maybe it's not a bearing that we would use, maybe it's something else. There's a video about the different types of threaded inserts you can use. There's some built-in features to be able to pause a print. So I wanted to do this as a live example, but I don't know that I've got time for it since I'm already running late. But we imported this crowned pulley and we wanted to put these bearings inside of it. And so basically we, let me see, where's the, I guess I don't have the Onshape link. I'll add the Onshape link for this before I put it out in meeting recaps. But if you drive this part, you can add in a sketch and revolve it around. And then as we printed it, this was like the bottom over here on the left-hand side. So you print up, and then we added a pause when it finished this layer. I'm sorry, we added a pause when it got to the end of the first bearing here. And before it started adding anything else, we put in the bearing. And that way, that bearing is now, you can see it's in here. You wouldn't be able to get that bearing in here any other way. You wouldn't be able to do that with a lathe or anything either. You would have to have multiple parts somehow to do that. So that's something that's very cool that you can do with 3D printing as well. There's this neat idea here of basically he 3D printed things to help give consistent bends to his parts for a press brake job. I don't know that that's something that we would necessarily do, but it may be give you some good ideas for things. And so that is it for the presentation. I am going to pull up Prusa here. And so what I would like is if, I don't know, I can kind of just talk it, but I wanted y'all to kind of think about these different parts and how it is that you may want to lay them down to be able to print something. So for instance, if we were printing this wheel encoder here, you would probably want pretty good detail on these encoder teeth. So it would not make much sense to try to print it say like this, because if you printed it like this, your layers would be really weird. And you would not get good consistency on what your gear teeth look like here. And also, like, you, come on. If you print it here, now you're kind of minimizing your supports, versus if you, instead of printing it this way, now you've got to add supports that come up all the way here. So let me maybe move some things back in here real quick, just so I can slice this as an example. All right, so as you can see, if you did this, now there's a ton of support underneath here versus, oh, I guess maybe I should explain real quick what's going on in here. So this is Prusa Slicer. There's these tabs up here that allow you to change some settings about things. Typically what you can do though, is you can select your print settings. So on our computer, we have these presets that you can use. And so we can usually do speed or draft and get something printed quickly, because we don't often need the full detail of it. And then you would select what kind of filament you have, because that sets all the temperatures and things like that. But say that we switched filaments, or we were having a problem with a particular filament, then you may want to go to the print settings, and you can change the, the filament settings, and you can change what your extruder temperature is. So maybe 215 is too hot. Maybe we want to bump it down to 210. Or maybe we want the bed to be a little bit warmer or cooler, things like that. And then for the print settings, maybe we've decided we need it to be stronger and we need more perimeters. So maybe we want 4 perimeters or 5 perimeters or whatever. And so you can slice it and see all that. You can change between the simple, advanced, and expert here. It doesn't change a whole lot that I've seen, but I haven't messed around with it a lot. And you can change your infill percentage directly from here as well. So, you know, increasing the infill will generally, again, give you a stronger part up to a certain point. You can decide if you want to brim on things here. And then there's this drop down for support. So if you have supports everywhere, they show up everywhere. I typically only do support on build plates. And so then these are all your parts. A lot of times, oh, I meant to actually just download a part. I feel like I want to continue this next time and maybe do a little bit of a full-on example of taking something from Onshape and bringing it into Prusa or Cura or Iker. So maybe that's what we do next week, is continue this. But you can see your different parts. Oftentimes, I feel like people end up downloading things with the wrong dimensions. They download it for inches instead of millimeters, and this expects it in millimeters. So you usually have to go and do the scale factors by 2,540%. And so anyways, you can see that there are a lot of supports there, versus if instead we came over here and put it like this, and there we go, and sliced it. It takes a second. Down here in the bottom right is where it would say slice now. And then this bottom left-hand corner shows like this is all your parts, and this shows it layer by layer. And then you'll get this drag over here, so you can see like where everything is. So this is showing layer by layer. You can see the default for Prusa is these curve wavy things instead of like the rectangles. And so you can see that this is with 50%, so it's a pretty high density. And you've got the holes, you've got your 5 perimeter walls, all that kind of stuff. So that's kind of a quick introduction to some of the Prusa slicer things. I also wanted to show this. So this is a pretty simple part. And maybe you think it doesn't matter if you lay it down like this or like this. But hopefully you can see that this side has this counter bore here. So if you were to print it like this, everything would be peachy and fine. If instead you were to try to print it like this, and let me slice it, I don't need to export it. You can see that when you look down at the bottom, you'd get these supports in there that just aren't really desired. So would it really cause any problem? No, it just might be kind of annoying to try to get those supports out when it's done printing. And then the last thing so hopefully things are sort of making sense with print orientation. This is another one that I'll kind of do as an example. So For ease of printing, this one, it might make sense to try to print it like, man, my mouse is not being very cooperative. It might make sense to say that you want to print it like this because you're minimizing your supports, you're printing things up. But the problem is now that your layers are this way, and if you can imagine, this was on that thrifty swerve, and so you might have a lot of forces trying to rip these legs off, and so it may not be very strong. So instead, if you print it more like this, now the layer when it prints, let me again show. I'll show both different examples here. Oh, I want to turn supports off for the moment. So now you can see that when it prints, it comes around and the whole thing can more or less end up being like all of this gives it all one layer or one print. And so it's very strong versus if instead you printed it this way. Now, if you can imagine, since this is a layer here and the layer adhesion is the weakest point, you could kind of rip this portion off of it much easier. So I'm way over time, so I'm going to go ahead and stop recording. I'm happy to take any kind of questions